Hello everyone. Today we are going to look at the continuation of fatty acid oxidation. So in the last session we learnt about how is lipolysis happening. Then we looked at the three stages of beta oxidation, that is activation, transport of fatty acids into the mitochondria, and then beta oxidation proper. We also looked at, apart from beta oxidation of saturated fatty acids, we also looked at beta oxidation of unsaturated fatty acids and polyunsaturated fatty acids. Then we also discussed about the energetics, that is how much ATP is produced by beta oxidation. So continuing with it today, we are going to be looking at regulation of beta oxidation, then disorders of beta oxidation. Then we look at oxidation of odd chain fatty acids and their associated disorders, peroxisomal oxidation and its disorders, and finally alpha oxidation and its disorders. So let us look at regulation of fatty acids. Now, at any given point of time, either beta oxidation should happen in the cell or fatty acid synthesis should happen. So there should be no futile cycles happening. That is, at one side we are trying to synthesize fatty acids and then the same fatty acids are being oxidized for energy. So these are futile cycles which should not happen. So we have mechanisms in place so that any one of these pathway only exists in the cell at any given point of time. This is mainly by hormonal regulation and allosteric regulation. So suppose we are in a well-fed state and the excessive acetyl-CoA that has been generated needs to be converted to fatty acids and stored for energy. So when fatty acid synthesis is happening, the first substrate, the first product that is going to be formed during fatty acid synthesis is malonyl CoA. So fatty acid synthesis happens in the cytosol and beta oxidation happens in mitochondria. So there is compartmentalization, so that both these are happening in different compartments in the cell. So that if beta oxidation has to happen, we have to transport the fatty acid into the mitochondria. So during regulation, malonyl CoA, which is formed during fatty acid synthesis, is present in the cytosol, which can inhibit carnitine palmitoyl transferase or carnitine acyl transferase enzyme. And this enzyme is required for transport of fatty acids into the mitochondria. So at the level of transport itself, regulation happens, so that when fatty acid synthesis is happening, beta oxidation should not happen. So malonyl CoA will bind at the allosteric site and causes a conformational change in the enzyme so that fatty acid cannot bind to the enzyme. So this is one way of regulation of beta oxidation. Now, as we saw previously, the requirement or prerequisite for beta oxidation is availability of free fatty acids. So for free fatty acids to be available, lipolysis has to happen. And in last session itself, we discussed how lipolysis happens. So a recap of the same thing again today. So when it is either epinephrine or glucagon that is present during starvation or when energy needs are high, the body requires energy. So that is when epinephrine, glucagon are going to be synthesized. So these bind to a receptor on the cell membrane, which in turn acts on adenylate cyclase and converts ATP to cyclic GMP. ATP to cyclic AMP. So this cyclic AMP in turn activates phosphorylates and activates protein kinase. So this protein kinase will in turn phosphorylate hormone sensitive lipase and make it active. So phosphorylated form of hormone sensitive lipase is active. So once this enzyme is active, this will lead to this will act on triacyl glycerides and release free fatty acids. So if the body is in a well-fed state and insulin is present, insulin will cause dephosphorylation, convert active hormone sensitive lipase to inactive hormone sensitive lipase and prevent lipolysis. So there is no availability of free fatty acid for beta oxidation. Instead, insulin is going to activate or stimulate lipogenesis, that is fatty acid synthesis. So the other way of regulation based on energy needs in the cell. If there is a high NADH to NAD ratio, this signals that there is enough energy and we are not utilizing the energy that is being produced. So a high NADH to NAD ratio inhibits acyl-CoA dehydrogenase and beta oxidation in turn will be inhibited. Now if there is accumulation of acetyl-CoA, we saw that in beta oxidation it is sequential removing of acetyl-CoA molecules. So if this acetyl-CoA is not utilized, that is it does not enter TCS cycle, or TCS cycle is inhibited because of high energy status. Again high NADH NAD ratio will also inhibit TCS cycle. So accumulation of acetyl-CoA, this in turn will have a feedback inhibition and inhibits beta ketothiolase. So this is the regulation of beta oxidation. One is by malonyl-CoA, which is allosteric regulation. Then we have hormonal regulation by glucagon epinephrine or inhibition of beta oxidation of lipolysis by insulin. Then we have high NADH ratio and increase in acetyl-CoA inhibiting beta oxidation. So now moving on to disorder associated with this beta oxidation. So this is the enzyme acyl-CoA dehydrogenase, which is the first enzyme. So if there can be a deficiency of acyl-CoA dehydrogenase, and as I told you last time, we can have multiple isomers based on the chain length. So you have short chain, medium chain, long chain acyl-CoA dehydrogenases. So of these, it is the medium chain acyl-CoA dehydrogenase deficiency that has been recorded most. This is an autosomal recessive disorder. So usually manifestation will happen after a prolonged fasting period, because initially the body will depend upon glycogen stores for its energy purposes. So when fasting is prolonged beyond that, or glycogen stores are depleted, that is when we turn towards beta oxidation. So during symptoms will be seen after a prolonged fasting period. So the mutation here is in the enzyme, lysine is replaced with glutamate. So manifestations will be vomiting, lethargy, coma, and this is one of the causes for sudden infant death syndrome. So this sudden infant death syndrome is an umbrella of disorders in which there is crib death happening to children. That is, the baby is doing fine. After feeds, the mother puts the baby to sleep, but in the morning the baby would have died during sleep. So this is sudden infant death syndrome, and acyl-CoA dehydrogenase deficiency is one of the causes for sudden infant death syndrome. The other feature that we see here will be dicarboxylic aciduria. We'll look at what are dicarboxylic acids when we come to omega oxidation. So here, because beta oxidation is defective and beta oxidation is not happening, the body will in turn follow the omega oxidation route, which results in the formation of dicarboxylic acids, which are going to be excreted in urine. So the Management here would be to avoid prolonged fasting, avoid strenuous exercise, and to take frequent meals, small meals at frequent intervals. So this way it can be mitigated. Now, beta oxidation is what is predominantly the source of energy for animals which are hibernating. Now, I'm sure you would have heard of this about the camel's hump. People tell that there is water stored in the camel's hump. So, what do you think is there in the camel's hump? So, this is something I want you to find out and tell me in class when we have this session. Okay, and I also want you to read about metabolic water. What is metabolic water? Okay, now we'll move on to oxidation of odd carbon fatty acids, odd chain fatty acids. That is, previously what we saw were fatty acids which had even number of carbon compounds, that is 16, 14, 12 or 18, 20, 24. These are even chain fatty acids. And beta oxidation is going to remove sequentially 2 carbon atoms as acetyl CoA. So ultimately a 4 carbon compound enters into beta oxidation and we get 2 acetyl CoAs. But if we start off with an odd chain fatty acid, so suppose we are looking at a 17 carbon fatty acid, which will undergo 7 steps of beta oxidation. Finally, it is a 5 carbon compound that is entering into beta oxidation. So when acetyl CoA is removed, we are going to be left with a 3 carbon compound, that is propionyl CoA. That is a 3 carbon compound. So there will be extra step that is required for metabolism of propionyl CoA. I'm sure you would have come across metabolism of propionyl CoA when you had amino acid metabolism, because if we look at sources of propionic acid, usually obtained during metabolism of the side chain of cholesterol or from odd chain fatty acids or during metabolism of isoleucine, valine, methionine, threonine. So during metabolism of these, propionyl CoA is formed. So I'm sure you would have come across the metabolism. You must be knowing the steps. Now, we do get some amount of propionic acid through diet because it's present in the mold inhibitor that is used while preparing breads and cereals. So coming to the metabolism of propionyl CoA, we are going to see how propionyl CoA can finally be channeled to form succinyl CoA, which can enter into the TCA cycle. So first step is carboxylation of propionyl CoA. So the source of carbon dioxide is a bicarbonate ion. Enzyme is propionyl CoA carboxylase and requires biotin as the coenzyme for this step. This is an energy requiring process and propionyl CoA is converted to methyl malonyl CoA, D-methyl malonyl CoA. Now this D-methyl malonyl CoA has to be converted to the L form. So we need a racemase which is going to have do molecular intramolecular rearrangement to convert D-methyl malonyl CoA to L-methyl malonyl CoA. Enzyme is racemase. And this L-methyl malonyl CoA by a mutase converts L-methyl malonyl CoA to succinyl CoA, and this requires vitamin B12 as the coenzyme. The succinyl CoA in turn can either enter the TCA cycle or can be used for heme synthesis or can be utilized for ketone bodies. Can be used for utilization of ketone bodies where it is the donor of the CoA group for utilization of ketone bodies. Now, disorders associated with propionic acid metabolism. So, there can be a defect in propionyl CoA carboxylase, the enzyme. So, if this enzyme is defective, there will be increase in propionic acid. Since it is an acid, it is called as propionic acidemia. Leads to increase in ketoacids in blood. So, usually presence within the first week of life leads to mental retardation and can lead to death early if it is the severe form. So, management would be to consume foods which are less in the amino acids which lead to propionic acid formation during their metabolism. So, then moving on, next is deficiency or methylmalonic aciduria. So, there can be two reasons for this. One is B12 responsive, that is a simple deficiency of vitamin B12 can lead to methylmalonic aciduria. So, if this is the case, on supplementing vitamin B12, symptoms should. If it is not happening, then it has to be the enzyme defect itself. So, here manifests as growth retardation, CNS damage, and it is a fatal disorder. Again, supplementation of B12 and dietary restriction of those amino acids which lead to formation of propionic acid will be the treatment. Now we move on to peroxisomal fatty acid oxidation. As I told you, the very long chain fatty acids will first undergo oxidation, beta oxidation in the peroxisomes, and after the chain length has reduced, it will move into the mitochondria. Here, there is no requirement of carnitine. Carnitine is not required for transportation. So, what are the differences between beta oxidation in peroxisomes versus beta oxidation in mitochondria? So, in peroxisomes, electron transport chain is not available. So, whatever FAD is getting reduced to FADH2 has to be reconverted back to FAD. It is not going to enter into the electron transport chain. So, instead, the reduced FAD will reduce oxygen to hydrogen peroxide and FAD gets oxidized to FAD. So, there is regeneration of FAD. The hydrogen peroxide that is formed can be neutralized by catalase to form water and oxygen. Okay, so this is one difference between beta oxidation in mitochondria and peroxisomes. So, there is no energy going that can be produced in the peroxisomes. Next, even the NAD that is getting reduced to NADH will get re-exported and then oxidized and is transported back to peroxisomes. So, there is less amount of energy that is going to be formed in the peroxisomes. So, whatever acetyl CoA is finally formed has to be transported out and has to be utilized. So, peroxisomal beta oxidation can be induced by a high fat diet or by certain hypolipidemic drugs. Now, coming to disorders associated with this. So, Zellweger syndrome. In Zellweger syndrome, the person is not synthesizing peroxisomes. So, this is a major disorder. So, it is a lethal disease because the hydrogen peroxide that is formed is required for combating infections, respiratory burst is required for combating infection. So these people are at a higher risk for infections and they can be more severe. Whatever small infection turns severe. And the very long chain fatty acids are not going to get oxidized. So these in turn will accumulate in brain, kidney and liver. So it leads to abnormalities in these organs. Lifespan is usually about 13 weeks. Next is X-linked adrenoleukodystrophy. This usually affects, because it is X-linked, it will affect boys. Loss of vision, behavioral disturbances are seen. Here there is a lack of transporter for very long chain fatty acids. So there is accumulation of very long chain fatty acids and death will occur in a few years. Coming to the last part, that is alpha oxidation. No, sorry, not last. After this we have omega oxidation. Alpha oxidation is another alternate pathway mainly for certain plant-based lipids. Okay. Here in alpha oxidation, it is removal of one carbon as carbon dioxide, as against in beta oxidation, removal of two carbons as acetyl-CoA. So here it is removal of one carbon at a time as carbon dioxide. This happens within the peroxisomes, mainly for plant-based lipids. One example is phytanic acid. So why is alpha oxidation required? Why not beta oxidation? So if you look at the structure of phytanic acid, if this is the carboxyl group, this is the alpha carbon atom and the beta carbon atom. At the beta carbon atom, there is a methyl group that is present. So this methyl group will prevent beta oxidation from happening. So that is why there is an alternative pathway, that is the alpha oxidation. So first step is a hydroxylase reaction, phytanic acid hydroxylase. Water is required and there is a hydroxyl group that is formed on the alpha carbon atom. And the carboxyl group is released as carbon dioxide. Removal of one carbon as carbon dioxide. Next step is phytanic acid alpha oxidase, which again the hydroxyl group that was present here is now converted to a carboxyl group, and the methyl group which was in the beta carbon atom is now on the alpha carbon atom. So the beta carbon atom is free to undergo beta oxidation. So there will be further cycles of beta oxidation till it reaches the next methyl group being present at the beta carbon atom. So it undergoes 6 more cycles of beta oxidation, and after that we finally release propionyl-CoA, acetyl-CoA and isobutyryl-CoA. Propionyl-CoA, we have seen how it is getting metabolized. So this does not require oxidation. Another difference when compared with beta oxidation. So there we required activation to form acyl-CoA, whereas here directly it can be used without oxidation. And carbon dioxide is released. So there can be a defect in alpha hydroxylase, phytanic acid alpha hydroxylase. This will lead to Refsum's disease. So here there will be accumulation of phytanic acid in the brain, leads to neurological damage. Coming to omega oxidation. So in omega oxidation operates in microsomes and in some bacteria, minor pathway for fatty acids becomes mainly important when beta oxidation is defective. Okay, here, so we have the carboxyl end and the omega carbon at the methyl end. So first step is a oxidation step where the methyl group is converted to a hydroxy acid. Okay, in the next step there is a dehydrogenation, and the hydroxy acid is now converted to a aldehyde group, and this aldehyde group undergoes further dehydrogenation to form a carboxylic group. So we now have a fatty acid where at one end there was a carboxylic group already. Now we have synthesized a carboxylic group at the other end. So that is why these are called as dicarboxylic acids. So when there is a defect in beta oxidation, it goes in for omega oxidation, forms a dicarboxylic acid, but because the beta oxidation is defective, it cannot continue with beta oxidation from the other end also. So that is why there will be increase in dicarboxylic acids which get excreted in urine, called dicarboxylic acid urea. Okay. So I think that brings us to the end of beta oxidation of fatty acids. So we have looked at oxidation of saturated, unsaturated fatty acids, activation, transport of fatty acids, then peroxisomal oxidation, alpha oxidation, omega oxidation. We have also looked at beta oxidation of odd chain fatty acids. So, and we have looked at the disorders that are associated with these. So I guess when I see you in class, one thing I told you to read, maybe you know about metabolic water. Then I asked you what is there in the camel's hump, and there are actually two interesting court cases which happened in the US, which has some relevance to beta oxidation and its disorders. So let me see if you can find out which are the two cases I am referring to. These were convictions which were made against the mother of the baby for murder. So the mother was convicted of murdering her own baby, and then it came to light that it was that she did not murder. So there are two such cases that I am referring to. So let me see if you can find out which are the cases that I am referring to. Okay, so I hope you will listen to this material or at least read from the book, so that when you come to class we can have a discussion, because I don't want to have a didactic lecture. Okay, so that brings us to the end. Thank you.